given you in previous class. So I asked you to find the solution, find the step response for these transfer functions. So this is the solution. I hope you are getting the same. What you need to do is just find the step response by putting Rs equal to 1 by S, right? So just substitute Rs equal to 1 by S. So Cs becomes, for the first um, transfer function, it becomes 24.542 divided by S square plus 4S plus 24.542 into S, right? So then by partial fraction expansion, you can find out the inverse Laplace transform, and that will take this shape, right? Okay. So similarly, you can find out the step response for T2, which is basically a third order system. And if you substitute Rs equal to 1 by S, it becomes fourth order system, right? So it will become 245.42 divided by S into S square, S plus 10 into S square plus 4S plus 24.542. Okay, so it becomes from third order to fourth order system, right? So for that also, because you can convert this S square plus 4S plus 24.542 into linear fraction. So by using partial fraction expansion, you can find out the factors of T2 and then find out the inverse Laplace transform, right? So you can do it, and the answer is this. I hope you are getting the same answer. Similarly, you can find out the partial fraction expansion of this third transfer function. This factor remains the same for all three transfer functions. Therefore, this you can, if you have done for the first, then you can do it for the second and for the third also, right? So the three responses are plotted further, and it is noticed that C2 with its third pole at -10 and further from the dominant poles is the best approximation of C1t, and the pure second order system response, and C3t is a third pole close to the dominant pole, which yields the most error. So you can find out the step responses, and they will come out to be like this. This is for C1. This curve is for C1t. This curve is for C2t. This curve is for C3t. And this I have shown you the MATLAB Simulink model of the given system, right? This is the transfer function. This part of the system is same for all three transfer functions, and these are the only gains are um, changing and making the system higher order systems. Okay, so in MATLAB Simulink model, as shown in the figure, there it can be used to plot the different three plots, right? You can just run this from this tab and substitute the input as a step of 1 volts, and then you can just run it for 3 seconds, and you will, if you click on this scope, you will get these type of responses. Okay, so if you can this is your home assignment, then you can find out the step response for this kind of system using MATLAB Simulink model. Okay. So now let us do another example. This example also I had given you in the class for home assignment. This is G1 is 700 upon S plus 15 into S square plus 4S plus 100. Okay, so the second order approximation for G1S is valid since the dominant poles have real part of -2. If you find out the partial fraction expansion of this, you will find out that one of the pole lies at -2 and the higher order pole is at -15, which is more than 5 times further. Okay. The second order system G2 is not valid since the dominant poles have a real part at -1 and the higher order pole is at -4, which is not more than 5 times. This I had already told you in the previous class that this is a rule of thumb that we can, if the dominant poles and the other poles of the systems are located 5 times further away from the dominant pole, then the system is valid and the system is stable, otherwise it is not. So wherever this condition is met, the system is valid, otherwise it is not. All right. So you can find out the response like this, right? You have to take the normalized. This is 0 at -3, 0 at -5, 0 at -10, and this system does not have a 0. Okay, so this graph shows the effect of zeros on the system performance. Okay, so the zero of a response affect the residue or amplitude of the response component, but do not affect the nature of the response exponential, right? So it is, if it is damped sinusoid, then it remains damped sinusoid no matter where the zero is located. All right. So the figure shows the normalized response of a second order system with zero at -3, -5, and -10. We see that the closer the zero is to the dominant pole, the greater is effect on transient response. All right. So let us analyze the situation by considering the following second order system with a zero. Right. So suppose this is the transfer function s plus a upon s plus b into s plus c. Then you can find out the partial fraction expansion like this. Then you can find out, you can substitute it like this. And if the zero is far from poles, then a is larger as compared to b and c. In that case, you can substitute this as a upon s plus b into s plus c. And the zero looks like a simple gain factor and does not change the relative amplitude of the components of the response. So please draw this diagram and write these expressions. I'm giving you some time. All right. Suppose we are having a system response with zeros, which is a non-minimum phase system. So a non-minimum phase system is the one step response of a second order system with a zero in the right half of the S plane. Such type of systems are called non-minimum phase, in which the response begins to turn in the opposite direction of its final value. So this is non-minimum phase because the response is in the opposite direction of the final value. This is the final value. Final value we have assumed to be 1 unity. So if the response initiates in the negative direction, then it is called non-minimum phase. If a motorcycle or an aeroplane was a non-minimum phase system, it would initially veer left when commanded to steer right. Right. So it will give a negative response initially, and then it will increase its initial negativity, and then it becomes the positive and gives the desired solution. Right. So such type of systems are called non-minimum phase systems. Okay, let us take another example with pole zero cancellation. Suppose a 3-pole system with a zero as shown in figure, right? Sk into s plus z is the zero of the system upon s plus p3 plus into s square plus as plus b, right? If the pole are located at -3, minus p3 and 0 at minus z, cancel out each other, right? Suppose this factor cancels out with this factor, we are left with the second order system k upon s square plus as plus b. So pole zero cancellation can also be performed if the pole is very close to the zero, so that a partial fraction expansion will show that the residue of the exponential decay that corresponds to the non-dominant pole is much smaller than the amplitude of the second order response given only by the dominant poles. So let us take another example. You can write it down. I'm giving you for some time. So this is how we deal with a system in which poles and zeros cancel out each other. All right. So please note it down.